So we've talked about the idea of learning, and for learning, just the idea is that an agent learns if it improves its performance on future tasks after making some kind of observations on current tasks, right? So it's doing something, it makes some observations about the world, and if somehow that leads to improvement in the future, that's learning. As far as learning is concerned, we have, well, the idea of improving the performance, there's changes being made then to the agent. Something is changing. It's either changing something about a component of the agent, it's changing something about the way it behaves as a result of something. And as far as the factors that are concerned, is we want to question which component of the agent is possibly able to be changed. What prior knowledge does the agent have? How is the data or the component itself represented? That has an effect on how things happen. And then what feedback is available? So what does the agent use in terms of feedback? And so with the feedback, we mentioned unsupervised learning. Unsupervised learning, we're not specifically telling the agent what's right answers and what's wrong answers. Right? The agent is exploring learning patterns, whatever, seeing what's happening. And in reinforcement learning is kind of the way the genetic algorithm works. At the end of something, it gets back some kind of feedback. If you're playing chess, it says you won. You get the +2 whatever for winning the game of chess. If in the genetic algorithm you get back this entity, this member of the population gets a score. We don't know why it got that score. Right? The genetic algorithm doesn't know why it got that score. If your AI wins the game of chess, it doesn't know which particular action led to that reinforcement, led to that positive thing. If there's a negative reinforcement, if it loses points or loses something, it doesn't know what specific activity caused that.
So in an unsupervised environment, the AI is not receiving feedback?
Well, so the AI doesn't receive any formal kind of feedback. There might be something from the environment, but it's not really receiving feedback in that kind of way. Now, what happens in a lot of situations, it's unsupervised learning, where we're not giving, we don't know the right answers for training purposes and so on. That's where supervised learning comes into play. In supervised learning, we have some kind of training set. We have something that says, here's what we're looking for, here's what's supposed to happen. But unsupervised, there might not be any feedback. It's just gathering data and analyzing connections between things and seeing what kinds of relationships exist between this thing and that thing.
Have you heard of GPT-2? Google's deep learning algorithm AI?
I have seen like a headline or something, but I don't know anything about it. So unsupervised situations are really where you're gathering data and analyzing that data, trying to find patterns to see if anything exists. There's not a right answer. There's not a wrong answer necessarily. It's just, is there a connection? Is there something here? So that's often used in those kinds of situations of trying to see what can we find out. Supervised learning is the scenario where you have, usually we're using this in kind of classification systems that we've talked about, the idea of saying this thing is in this category. And so what we'll do is we'll have this kind of collection of input-output pairs. And these inputs or the outputs might not be, this isn't necessarily a one-dimensional kind of thing. This might be a multi-dimensional input, a vector input, and then some kind of output. So you're going to have these collection of pairs in the supervised learning. And there is some kind of function that takes that input and gives that output. And the task in supervised learning is to figure out the function.
So the classic example is if images of two different types being given to the AI, and AI has to try and figure out which ones are which type.
Yeah, and so we would have lots of different images that fit into the different types, and we're trying to figure out a way to calculate from this input what is the output. Now, I said figure out the function. What often happens is we figure out kind of the best approximation, right? It's not necessarily figure out the function that does this. It's figure out a pretty good function that gets it right most of the time. And then what will we do? Then we will take that and utilize that in a new environment that's not based on the input-output pairs that we already have. It's just based on new inputs. And we say, okay, well, the system says the output should be this. And depending on how good the system is, then maybe that's right, and maybe it's wrong, and we do what we will with that end result. So as far as learning goes, unsupervised, reinforcement, supervised, real-life situations often blur the lines. There's some supervision and then some unsupervision and maybe some reinforcement along the way and different things going on. But why don't we just write our AIs to not need to learn, to just know the information to begin with? Because we have to know it ourselves, and then we have to figure out how to implement that, right? And so often we don't have any idea how to do the task, and even if we can do the task, doesn't mean we know how to tell a computer how to do the task. And so, so the learning idea is kind of vital to all of this. Now, we're going to today talk about the first portion of neural networks, and this is actually where AI kind of started, trying to mimic a brain, trying to mimic neurons. And after a period of time, it fell out of favor because a certain problem couldn't be solved, and we'll solve it today. But a certain problem couldn't be solved, and so people kind of got distracted and went away from things and then came back around. And also, the computing power being available to solve certain tasks just wasn't available early on. Excuse me. And so what happens in real life situations, even when we have, say, supervised learning, what happens in supervised learning? One thing that I've seen a task of trying to figure out just from pictures of people how old they are. All right, so what do? You have pictures of people, and you have their age. You feed that into the system. Here's a picture, and here's the right age. And the system's trying to learn that. And what might happen? In all that data, there might be some noise. Somebody misentered the correct age. But there also could be systemic failure in the fact that some people could have just lied about how old they were. And so even though it's ostensibly supervised, in a sense it's unsupervised because you don't really have any correct kind of feedback going on. So noise, lack of labels or mislabeling, all of those kinds of things can put us somewhere else. So what we hope for, if we're doing supervised learning, is that the input-output pairs are actually matched correctly. So when people are doing this kind of thing with handwritten characters, we talked about that. We hope that the characters are labeled correctly. But have you ever read something and not sure what it is? So if you were tasked with labeling certain letters that were handwritten, you might get some of them wrong. I mean, depends on how well they're written. And so sometimes we might get some things wrong. We also might misenter something. So there can be those kinds of errors. And what does the system do? The system, in that case, does the best it can with what it has. Now, what if it's really poorly labeled and it's still supposed to be supervised? Then it probably would have been better to be not labeled at all and let the system just try to figure, oh, these are the same. I don't know what they are, but they're the same. And that's what unsupervised learning might do. Give it a bunch of characters, and somehow it figures out that these characters are the same and these characters are the same and they're different than those, but we don't know what, it doesn't have any way of specifying what they are. So in this input-output pair, this approach that we're looking at today, that's exactly what we're doing. We are going to have a bunch of inputs and the corresponding output, and we're going to figure out what happened in between. Now, the kind of models you can use for learning, there are linear models, there are nonlinear models. What does a linear model do? A linear model, if you have this kind of change in the input, you have a corresponding same size change in the output, right? That's a linear function. It has to do with the slope and so on, right? You change something here and you know exactly how big of a change is going to happen on the output. What happens in a nonlinear model? In a nonlinear model, small changes in one place can lead to big changes somewhere else. So you change the input a little bit, it can change the output a lot. And so nonlinear models correspond, and what a nonlinear model that we're going to build, a neural network fits into that category. You can change the input a little bit and possibly change the output a lot. Other kinds of things, non-parametric models, there's something called support vector machines that we might talk about a little later. A lot of different kinds of models. And it turns out, again, in real life, that mixed models tend to do better than a specific type of model, for lots of problems at least. All right, so we're going to do the supervised learning approach where we have a training set. And a training set is going to consist of some collection of things. The inputs, these x1, x2, x3, these could be vectors, right, in terms of multi-valued things. The output could be a single value, could be multi-valued as well. And but it's given this input, then we get a particular output. And the idea is that each y is some function of, well, not like that. Say it this way, that each y is generated, so the x is over all possible x's, right, whatever the input, and the y. So each y value is generated by some function. And our goal is to try to find some new function, h, that comes as close as possible to that function. In some cases, we can discover an exact function that gives the right answer every time. In most cases, we can just discover a function that does a pretty good job. And pretty good will depend on our context, and we will change that. All right, so the basic component of this, in terms of a neural network, is what's called, well, there's a few different names that have been given, but this is one of the early names, and this is the kind of name that has stuck, a perceptron. A perceptron has some inputs, how many ever inputs we need. Those inputs have various weights. Those inputs are taken in, and a calculation is performed. There's a mathematical calculation that's performed, and then there is an output. And so the inputs, we have whatever we have here, we have a corresponding weight. For the inputs, I've left this one down here blank for a reason. In this kind of model, there's always an extra bit that we deal with called the bias. And the bias is a value that gets added into this total later, as part of the calculation. And a way to describe that is by putting a dummy input of 1 and then having a weight here which corresponds to the bias. And usually if you see it done this way, this is like the index 0 add-on, but there's an extra value that's attached. And this corresponds to the bias. It's a way to have an extra factor that you can push the answer in the correct direction and have some leeway for nudging an answer this way or that way as appropriate. Okay, so in here, there is something, threshold function, and I just realized I don't know how to spell threshold. 1H or 2 H's, I don't know. Anyway, a threshold function. So there's a calculation that will take place. So we're going to see a couple of different functions that are involved here. One function that gets included in this is sometimes called the Heaviside function. The Heaviside function is named after a person named Oliver Heaviside, lived in he was born in the 19th century. Did a lot of work in a lot of different areas. Part of one thing that he did was things with electricity, magnetism, some things with like telegraph systems, and a bunch of different kind of work. Interesting guy. And so the Heaviside function says what we're going to do is we're going to look at this input vector. So I'm going to write it as a vector with the arrow just so we can emphasize. This is the input vector. And the input vector, I'm going to throw that dummy part of 1 as part of that vector. Right? So it's not an actual input, it's a fake input, but it's part of the system. So I'm going to include that in the input. Sometimes when we draw these or write these, we'll do it in a slightly different way. And then we have this collection of weights. And so there's several weights, and that's also a vector. So this is a vector of inputs. And W, we'll say, is the vector of weights, including, in this case, we're including the bias weight as one of those. Again, sometimes we separate that out, but it does the same result in the calculation. All right. And then what we will do is we will calculate the dot product of those two. So we're going to take the input and its corresponding weight and do something with that. So the Heaviside function that we usually call H of the input value is, for our purposes, we're going to do this in a strictly binary approach. So we're going to have a 0 or a 1. But the function is defined in that way, as a 0 or a 1. So the perceptron, which is like a single neuron, either fires or it doesn't fire. So it's either off or it's on, well, on or off, right, in that direction. It either fires or it doesn't fire. It gets some input, and it either triggers it or it doesn't trigger it. And so we're going to get a 1 or a 0 as the output of the perceptron. And so there's a couple of different ways that the decision can be made here. The idea is if x dot w, and usually it's if it's greater than 0 or not, and we don't focus quite as much on if it's equal to 0, but we decide what happens when it's equal to 0. So in some cases, we say if this is greater than 0, we do that, and if it's less than 0, the dot product is less than 0, we do that. And if it's equal to 0, then we make a decision. Either we put it as 0 or 1. Sometimes it's even done as like 1/2, some other possibilities. For our purposes today, I think that we can avoid 0 altogether. So we can make sure that all of our values miss 0. But otherwise, if we wanted to have a completely defined function on all possible inputs, maybe we say if it's not negative, the output is 1, and if it is negative, the output is 0. Or we could put the or equal to in the other place, or like I said, we could leave it out completely. We could put something else in. We could put it in as 1/2 if we like. There are reasons for making different decisions, and those decisions can matter. But for our examples today, they won't matter. All right, so what's the idea of a single one of these? We have these inputs, we have these weights. We do this calculation, and we either get 1 or we get 0. Either that perceptron fired or it doesn't fire. And what we want to do is we want to be able to do logic with this kind of system. So we want to be able to come up with the appropriate weights that will allow us to do logic operations. I don't know why I erased that part. So let's think of OR. Actually, we'll do not in a minute. It's simpler, but I've already written OR down, so let's go ahead and do OR. OR has how many inputs? An OR statement has 2. So we're going to have 2 statements, and then we're going to throw in our bias value. So we're going to have 3 inputs for the perceptron. One of them, is this fake input, but is part of it. All right. I'm going to go ahead. I'm going to write these with index notation because it's a vector. And we have values that are going to go here. And then we have a particular output value that happens here. All right. So we are trying to figure out a function that will take certain inputs and give us the correct output. Now, what do the inputs look like? The inputs are statements that are true or false. Right? So we have trues and falses, and we get out a true or a false. But we can think of those as 0s and 1s. All right, so we are going to put in statements for the A or B, the truth values, 0s or 1s, and then we need to get out the correct 0 or 1 value over here. And there's weights associated with that. So what is the function that we're trying to create or trying to deal with? Well, all of this is a function. We need to know the correct, the inputs are fixed. The output is fixed. It's supposed to be the right answer. So all of these weights are really describing the actual function. So we have to figure out what the weights are. And we're going to do that based on our training data, our set of information. I need to keep that, and I am limited because I had to use this wired microphone, so I can only go so far. All right, let's try here. For OR, if we have, say, a statement A and a statement B, then A or B. So what do we have? We have true and true. A or B is true. True, false. False, true. And then false, false. Okay. And so if we think of these in 0s and 1 terms, what happens? What happens if I put 0, 1? Well, this corresponds to A, let's say, and this corresponds to B. And so what is this? Which row are we looking at? We're looking at the 3rd row. So what output do we need? We need our output, in this case, to be a 1. And we need to figure out what weights to put on here in order to make that happen. All right. I'm sorry?
just give it to the AI and the AI can...
Well, so the AI can only figure it out if we tell it how to use that information. If we tell the AI how to use the information, then it will be able to figure it out, and we'll do that in a minute. But for right now, let's see if we can figure something out. Yeah, so what are we going to have? We have vector x. I'm going to write it like this. That's vector x. Vector w, I put that at the end. That one is this one. Again, we could have put it at the beginning, wherever, right? Just as long as we know which one is the bias. And since I did call it W0 over there, I'm going to go ahead and call it W0, even though it's at the end. Anyway, maybe we should just call it B for the bias value, the bias weight. Right? But that's part of this vector. So what are we looking at? We need these weights to, when we do the dot product, we need that value to be, we want it to be positive. All right, so what are we looking for? We're looking for 0 times W1 plus W2 plus B, and we really want that to be positive. So are there any weights that we could put in there that would make that positive? Okay, so what happens? W1 can be anything, so let's just say 1. W2, can W2 be negative?
Yeah.
As long as B is greater in absolute value, right? So W2 could be -1 and B could be 2. And that would give us the right output. Right? Now, as far as this one input is concerned. Now what happens if we switch inputs? Then it might not give us the right output anymore. But for this particular one, it gives the right output. So what happens usually in this process is we actually start with random generation of some weights. And then we'll have the system, we'll build in how it takes that information and what it does with it, and it will adjust those weights until it gets to something that works. So as far as this is concerned, for this particular input, it gives the right answer. Now let's change inputs. Let's put this input in. So now what happens with this input? It's the vector changes to 1, 0, 1. With those same weights now, what's the dot product? It's 3, which is still good, right? These weights still work for that value. All right, well, what do? We go through all of these. What happens in this case? All right, then this would change to 1, 1, 1. And it's still positive. So we're still good. Let's do this one. All right, so now we have 0, 0. And what's the output in this case? The dot product is 2. So the function, the perceptron outputs 1 when it was supposed to output 0. So this is not a good set of weights. It works for 3 of the 4 possibilities, but it doesn't work for one of them. And so that's not a good set of weights. So what do we need to do? We need to change the weights, right? We need to change the weights somehow to make it so that it works for all of them. Does that make sense? Yeah, so there is, but for right now, right, what do we have? We have, this is what we're trying to do, and one way is to just try a whole bunch of stuff until something works. So let's see what has to happen. In this situation, we need that negative value down there, don't we? So the bias needs to be negative because otherwise, because you have these zeros here, and you need the bias needs to be a negative number. Okay, so what happens if I just swap that negative? Let's try again now, right? Let's see what happens. So, true, true, leads to what value? So the h value, well, let's do it this way. H of this. I called that a vector in that way. H of this vector let's see, so what are we doing? H of the vector says we have to do the dot product. So the dot product is 1 plus 1 minus 2, which is 0, which if we hadn't put the greater than or equal to 0 up there, then that's a problematic situation. Right? So it can be a little iffy if we want to actually do that right there or not. But the way we've written it, this output is 1. Let's try this one. That is, well, the dot product is -1, so the output is 0. And what was the output supposed to be? It's supposed to be 1. So what does that mean? The bias is too big in absolute value, right? It's too negative. Okay, so what if we took that or equal to part out completely?
Both of the weights 2 and the bias -1.
Okay, or since I don't want to rewrite all that, I could just make the 2 a -1/2, and it does the same thing, right? Okay, so what I did instead, so the -2 was too much. It made this answer be 0 when it was supposed to be 1. So I said, okay, well, let's try this instead. Let's make that bias not as extreme. Instead of making it -2, let's just make it -1/2. All right, let's see what happens. Dot product here, 1 plus 1 minus 1/2. That's still positive. Output is 1. Here, what do we get? We get 1 minus 1/2, which is still positive and gives the output that we wanted. All right, let's keep on going. 0, 1 is this 1 minus 1/2. So still positive, so we still get 1, which is what we wanted. And what happens if we put the zeros there, the two false inputs, then that makes the answer be negative, which means that we output 0, which is exactly what we wanted to output. And so what happens? Are there other functions we could have used? Are there other labels we could have put here? Sure. But what does this label do? This set of labels gives the right answer for every possible input.
A or B can be any weight so long as the bias is negative. The inverse of that is
So like if you, yeah, so long as we don't, so long as it needs to be negative so that this works, that does the right thing, and it can't overwhelm either one individually, right? So it can't be bigger in absolute value than either of these individual weights. Does that make sense? All right, so what have we done? What is this thing? I mean, we said it's a function, so it is, but I mean, it's a kind of weird-looking function. But let's think about what we have here. I wish I had the smartboard here. I could move that because I need to have that later, but I'm limited. So, all right, we'll write it down again later. point, one of these times when I pulled that, I unplugged the mic, so I don't know how much audio we have. I have all of this, but what? Lecture from last year, which is similar, probably. I don't know. All right, so does it sort of make sense? All right, now what do we need to be able to do? We need to be able to update these without having to look at it and think about it, right? We need to be able to write a program that can create a perceptron and update the weights itself without us having to tell it what the weights are. So we need a perceptron update rule.